Good morning. Welcome to Calculus with Z. This is lesson 3.10, related rates. Let's have some fun.
Okay, I'll be solving this problem about a ladder that's falling down a wall. It says a ladder 13 feet long rests against a wall. If the bottom of the ladder slides away from the wall at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet from the wall? So, to set up this problem, you have to visualize this ladder against the wall as a Pythagorean triangle with a right angle right there. And for the sake of this problem, this will be x, this will be y, this will be z. So, whenever you're solving this problem, you would want to set up the Pythagorean theorem. X squared plus y squared equals z squared. Where x is the ground, y is the wall, and z is the ladder. Then you would derive this whole equation, 2x, and then the change in x over time, dx over dt, plus 2y, dy over dt, equals 2z, dz over dt. And since there are these 2's everywhere, you can just cancel them. They are not necessary. So you're left with x dx dt plus y dy dt equals z dz dt. Now, to keep solving this, you would then plug in the values it gives you. It says that the rate of change of x is 2 feet per second, since x changes at 2 feet per second. So that would be your dx dt, which is 2. X, it asks for when it's 5 feet from the wall, so you would want 5. Then you would add y, and to find y, you would set up the triangle. You know the z is 13 feet, and
X is 5 feet.
And you know that the x is 5 feet. So, to solve this, you would do the square root of 13 squared minus 25, or minus 5 squared, which equals 25. So 13 squared minus 5 squared. And so what you would get from that is the square root of 144, which equals 12. So this would be 12 feet. So you would plug that in for y, because y is 12 feet whenever x is 5. And you're solving for the dy dt, so you would leave that as the variable. Now, in this case, it doesn't really matter what z is. It's 13. But because of the fact that it doesn't change, the dz dt is actually just 0. So this is just nothing. Cancels. Then you have 10 plus 12 dy over dt equals 0. Move it around. 12 dy over dt equals negative 10. And then you have dy over dt equals negative 10 divided by 12, which would end up being negative 5 over 6.
And if you think about it, it makes sense that it's negative because the rate is making the y value go downwards. So the ladder is falling, the top of the ladder is getting closer to the ground.
Absolutely.
So there you go. Thanks for watching Lessons of Calculus with Z with us. Okay, so what I'm gonna do here in a minute is explain to you guys some of the general approaches that we give to some of the problems with related rates. So the most common that we usually see is volume problems, like this cone tank problem. So what you want to remember is you have to differentiate what's constant and what changes, what actually has a rate. So in the case of the cone problem, you know that there's water dripping out, so the volume is gonna be decreasing. But you know, like what remains constant in this case is the ratio of the height and the radius of the cone of water that's inside. So you can pretty much figure out this ratio, and you know that if in the total radius on the full cone, the radius would be 3 and the total height would be 6, then you can figure out this reason and plug it into the main volume equation for the cone and go from there. So then there's a couple of other examples of volume problems, like this balloon problem. You pretty much assume it's a sphere and you have your equation for your sphere, and they're asking you find the r dt when r equals 5. So this is pretty straightforward, but you just realize that oh, the RDT is not actually constant because it gets smaller every time. So they have to specify you a time R to find the RDT, because otherwise it would be changing. And DVDT is constant. You know that you're filling the balloon at a constant rate, so you're good there. Then there's a couple of other problems, such as this shadow problem. It deals with angles, so you just have to realize that what's in blue here, the man's height, that's constant. The man is always measuring the same, and what changes is the shadow length. So they are asking you to find the speed that the tip of the shadow is moving. So you pretty much deal with d theta dt dx dt, but you can ignore the height there, the y component. And finally, this is one of my favorite problems, the rocket problem being observed by the camera. In this case, they're asking you two things. How fast is the rate of the rocket, like the distance, this z dt, the distance from the rocket and the camera changing? So you can find that, and then you have to find the rate at which you have to rotate the camera to still be focusing at the rocket. So you can find this d theta dt. And you assume that the rocket is moving only vertically so that the horizontal distance is not changing to ease things off, and that way you can assume that the x dt is 0 and everything that goes with x you can eliminate. Just like on that last problem with the staircase would always be 15 meters or 15 feet or whatever it was, and that just makes your life easier, so pay attention to that, guys.